Our size today somebody had requested in my pre-cal class cats with a bear hat. So here we have cats with bear hats. Today we're going to learn Taylor and Maclaurin series. I was looking, I couldn't remember how to spell Maclaurin, sorry. Maclaurin. The Maclaurin series is just a subset of Taylor series. So if we learn Taylor series, then we'll know Maclaurin series. These are two mathematicians that came up with the super cool stuff that I've sort of shown you before. Like if you have y equals sine x. Oh, and by the way, I will have sent you notes on this that you can follow along with, and then the worksheet that I'm going to be working. You'll have copies of those attached to the assignment for Tuesday. So Taylor came up with this way to write a polynomial to model sine x. So if I take f of x is sine x, f prime of x is cosine x, f double prime of x is negative sine x, and f triple prime, sometimes we'll go triple prime, is negative cosine x. But after a while it gets a bit ridiculous, so we end up going f4x equals back to sine x, and it cycles around there. Not sure you can read that, so I'll make it darker right there. So, I'm sorry, I didn't even show you why I was doing this. There's a formula for Taylor series. Right, the reason it's called a Taylor series is it's a sequence of terms added together. And there's an easy formula to memorize. You take f of c plus any given number c, a specific constant, f prime of c times x minus c to the first over 1 plus f double prime of c times x minus c squared over 2 factorial. This is 1 factorial, which is 1. F triple prime of c, pretend like that's a triple prime, of c times x minus c to the third over 3 factorial plus f fourth derivative at c times x minus c to the fourth over 4 factorial, on and on until you get f, whatever derivative you need, to the nth power times x minus c to the n over n factorial. I'll teach you a lot of tricks, but if all else fails, don't forget this easy formula. All right, let's get a clean slide and write it again. All right, so this is a Taylor series. A Taylor polynomial is what this is called. This is called a Taylor polynomial. Can't write. Okay, so you say f of c. Oh, and by the way, this is a polynomial centered at c. And so I'll show you what that means as we go. F of c plus the first derivative at c times x minus c to the first power over 1 factorial. We usually don't write all of that down, but that's what's going on. The first derivative, x minus c to the first over 1 factorial. That's a 1. Then we go second derivative at c, second power over 2 factorial. Third derivative at c, x minus c to the third over 3 factorial, and so on and so forth. By the way, this is called this one, to denote it, would be a p of c with a little 3 down here. That means a third degree polynomial. But it would also be an n equals 4 because it has 1, 2, 3, 4 terms. So to get the language down. All right, so if I have sine x, f of x equals sine x. We all know what sine looks like. In the interest of time, I will probably do it on, well, I'll do it on the calculator. While I'm waiting for that to come up, if it's not in the way of what I'm doing. Oh, here it comes. So be patient while I develop some of this, and then I'll teach you easy ways to know it. All right, so I'm sorry, we all know what sine x looks like. and let me make sure I'm in radians, and my window, I'm going to make it go from like -3 to 3 or -5 to 5, just so we can see this good sine wave right here. All right, so what Taylor found is, and I'm not going to show you the proof, but you could do this and it would give you a polynomial that would mirror this sine function, which is one of the transcendental functions. Transcendental meaning it's not a polynomial. All right, f prime of x is cosine x. F prime, double prime of x is negative sine x. F triple prime of x is negative cosine x. And the fourth derivative at x is back to sine x. All right, now what I'm doing right now is really sort of like the very first part of your notes on Taylor series at the very top of the page. I'm going to write a Taylor polynomial that will approximate the sine graph. And so what I'm going to do right now is I'm going to center it at 0, and I'll show you what that means in just a minute. So now I've picked 0. And by the way, if I'm centering at 0, it all of a sudden becomes a Maclaurin series. So a Maclaurin series, if I ever tell you that, that means you're centering at 0, okay? It's just a subset of Taylor polynomial. A Taylor polynomial can be centered at pi over 2. Let me go ahead and show you what the centered means. Here's sine x, or any, well, right now we're just talking about sine. Okay. If I write a Taylor polynomial, you'll see it start to fit on it around 0. Okay. But if it's centered somewhere else, you'll see it start to fit on it somewhere else on the graph, like if it's centered at negative pi or something. So it'll start to settle into it, well, not there, I'd have to turn it over, but it will settle into it wherever we center it. And it's better than a tangent line because it's a tangent curve, sort of, kind of, because you're taking all of these derivatives. Sorry. It's sort of like a tangent line, but it's a big old, huge, gigantic on steroids tangent curve. And so you can use it to approximate values further out, kind of even better than Euler's method, because it hugs the graph and converges onto the graph for a while. The more you write down here, the more that's going to model onto the graph and converge onto the graph, and you can vary further away from where you centered it if you wrote more, and it converges longer. We'll worry about all that later. We're just going to write one now. Sorry about all that talking. We're centering at 0. So f of 0 is sine of 0. F prime of 0 is cosine of 0. F double prime of 0 is 0. F triple prime of 0 is negative 1. And the fourth derivative at 0 is 0. And if I found the fifth derivative, it would have been cosine x at 0 would be 1. So now I'm going to use this little formula to write the Taylor polynomial for sine x. So this polynomial will hug sine x for a while, centered at 0. The more I write, the more it'll hug. All right, so I go f of 0 plus f prime of 0 times x minus 0 to the first over 1 factorial, plus the second derivative at 0 times x minus 0 squared over 2 factorial, plus negative 1, the third derivative, times x minus 0 to the third over 3 factorial, plus 0 times x minus 4 to the fourth over 4 factorial, plus 1 times x minus 0 to the fifth over 5 factorial. And right now I've just written a polynomial of x with degree 5. Polynomial of degree 5. Now if we clean this up, these zeros go away. This gives me 1x. This gives me minus x cubed over 3 factorial. This gives me plus x to the fifth over 5 factorial. If I wanted a higher degree or more terms, I would have minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. Okay, and so like this right here is the 5th degree Taylor polynomial with n equals 3 terms. It's got 3 terms. Now I'm going to, and by the way, you'll memorize this one, so you don't have to derive it ever again if I have sine x. All right, so I'm going to go to my calculator, and I'm going to type in the Taylor polynomial for sine. I'm sorry, and it's really actually the Maclaurin series. This one is centered at 0. If they're centered at 0, there's certain things that we can memorize. X to the 3rd over 3 factorial. And if these are hard for you to type in, remember you can use that little alpha y equals key to get a fraction. You can already see it starting to fit on it right here. I hope you see this. Plus x to the 5th, it'll converge onto it a little bit more. The series will converge onto the transcendental function divided by 5 factorial. Isn't that amazing how that works? Then that's going to be minus, let's do a little more, x to the 7th divided by 7 factorial. Oops, sorry. I think I forgot to put the 7 in. Let me go back out here. I didn't want to waste time. Over 7 factorial. And the more I go, the more it's going to converge onto the graph. You saw it just settle in as it was calculating. So you see, wow, I centered it at 0, sort of writing the equation of the tangent line at 0, but I'm writing the equation of the curve centered at 0. So it converges onto it more and more. The more I write, the more it's going to wrap onto this. And I can move further away from 0 for an estimation. Now, just a side note. Sorry, I'm not on the cat bears, but that's okay. Now we're going to memorize every time that we're writing a Maclaurin series or a Taylor series centered at 0 for sine. We don't have to rewrite it. It's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and it'll go like that. Some of you, I hope all of you remember that sine is an odd graph. It's an odd function symmetric to the origin. And notice that these powers and numbers are all odd. It's an easy way to remember it. Now let's write cosine. So f prime of x is equal to negative sine x. F double prime of x is equal to negative cosine x. F triple prime of x is equal to sine x. Fourth derivative at x is equal to cosine x. Fifth derivative at x is equal to negative sine x. If I centered this one, f of x equals cosine x. If I centered at 0, it's a Taylor series centered at 0, or I could just say Maclaurin series. F of 0 is 1. F prime of 0 is 0. F double prime of 0 is negative 1. F triple prime of 0 is 0. The fourth derivative at 0 is 1. And the fifth derivative at 0 is 0. So now I'm going to write the series. To write a Maclaurin series, you say f of 0 plus f prime of 0 times x minus 0 to the first over 1 factorial plus f double prime of 0 times x minus 0 squared over 2 factorial plus f triple prime of 0 times x minus 0 cubed over 3 factorial plus f the fourth derivative at 0 times x minus 0 to the fourth over 4 factorial and then the fifth one's just going to be 0. So anyway, watch the zeros go out, including that fifth term I didn't write. So I have 1 minus, this is going to be x squared over 2 factorial. This one's going to be 1x to the 4th over 4 factorial. Guess what the next one's going to be? Minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. That, I'm not going to graph it, but that will approximately equal cosine. In fact, if I go dot, dot, dot forever, it will equal cosine. Now we know cosine x is an even graph, symmetric to the origin. And notice all these even powers. This is x to the 0, x squared, x to the 4th, x to the 0, x squared, x to the 4th, x to the 6th, x to the 8th. So we'll memorize these two and we can use them. I don't want to get too far into this, but what's really cool is if you have to write a Maclaurin series for sine of 2x, I'm going to predict what it is. I know that sine of x, you can treat these actually like polynomials. I'm sorry, if they want you to do I'm going to say it right. If they want you to model sine of 2x, okay? I know that f of x, when f of x was sine x, when my variable or my argument was just x, after our work we did, we got x to the 1st minus x to the 3rd over 3 factorial, all the odds, x to the 5th over 5 factorial, x to the 7th over 7 factorial. What if we have this? The derivative of the first derivative is going to be 2 cosine 2x. The second derivative is going to be negative 4 sine 2x using the chain rule. The third derivative is going to be negative 8 cosine 2x using the chain rule. And the fourth derivative is going to be 16 sine 2x. If I'm doing Maclaurin series centered at 0, the sine of 0 is going to be 0. This one's going to be the cosine of 0 is 0 times 2, 1 times 2. The sine of 0 is 0. The cosine of 0 is 1, so I get negative 8. And this one goes to 0. So if I write the Maclaurin series of sine 2x, I get 0. Then I get plus, sorry, I lost my train of thought, plus my first derivative. So 2 times x minus 0 to the 1st over 1 factorial. I'll lose, so this is f of 0, f prime of 0, f double prime of 0 I lose, now I'm at f triple prime of 0. So I'm going to have minus 8 times x minus 0 to the 3rd over 3 factorial. Let's do one more. The fifth derivative was going to be 32 sine of, 32 cosine 2x. At 0, that's written so bad, that's going to be 32. So we lose our x to the 4th, and we're on an x to the 5th. So I get plus 32 x minus 0 to the 5th over 5 factorial. Let's see what happens here. 0 plus 2x, 8 over 3, 2, 1. Right here, 2 goes into 8 4 times, and so I get 4/3 x to the 3rd. I'm going to make a big deal about this in a minute. 32 over 5, 4, 3, 2, 1. Let's see, we have 8 goes into this 4 times, and so we get 4 over 15, I think. So then I have plus 4 over 15 x to the 5th. Let's go back to this blue. Don't forget that this is a polynomial, okay? So if I know f of x, look at this. What would f of 2x be? Let's fill it into our already found polynomial. F of 2x we'll go this far. And instead of x, I'm going to put in 2x. If you could read my writing, that's a 2. Ooh, that's horrible. This is a 2x. This works really well when you're doing a Maclaurin. So I have 2x minus. This is 8x cubed over 3 factorial. This one's going to be 32x to the 5th over 5 factorial. You can see without all of this work, I have an easier way to do it. That's going to be a big, big deal, okay? So let's see what we have so far. And I've sort of done the first, almost down to the bottom, about 2/3 of the first page, I guess. All right, so you should memorize that the Taylor polynomial for sine x is equal to the odd ones, x minus, and they alternate, x minus x to the 3rd over 3 factorial starts with an odd, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, dot, dot, dot. Cosine x is even. It starts with x to the 0, so it's 1x to the 0 minus x to the 2nd over 2 factorial plus x to the 3rd over 3 factorial minus x, sorry, that's wrong. Do your evens. Every other one, x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And you do not have to derive these. You can go in with them memorized. And I'm going to go in and give you e to the x on this page, and then we'll verify it. 1 plus x squared over 2 factorial. This is the Maclaurin, which means it's centered at 0. X to the 3rd over 3 factorial. X to the 4th over 4 factorial, dot, dot, dot. So have these memorized. These 3, they're on your study guide for BC before you go in there. And you are welcome to use them. You don't have to derive them. Let's derive e to the x. So if y is e to the x, y prime is e to the x, y double prime is e to the x, y triple prime is e to the x. And if I calculate those at 0, they're all going to be 1. So if I start off with f of 0 plus f prime of 0 times x minus 0 to the 1st over 1 factorial plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x to the 3rd over 3 factorial, dot, dot, dot. So notice e to the x has all of them and it doesn't alternate. Sine has the odds, cosine has the evens, they alternate. So, and we can fill all sorts of things into those that you'll see if we memorize those. All right, some people memorize the next one. It's just sort of up to you. You can always derive them. I'm giving you the wherewithal to derive it. There's some in our book that tell you, like, oh, by the way, I don't know that I would necessarily memorize this one, but I think it's in our book in a chart as some of the stuff people memorize. But I'm just going to derive all the rest of them. Now, this is centered at 1. ln x looks like this. It's even undefined at 0, so I can't center it at 0 anyway. This one's centered over here, and it's going to start to, the polynomial will start to morph onto that as it goes. So this is centered at 1, so it's just a Taylor series. I could only call it Maclaurin if it's centered at 0. Sometimes they'll just say a Taylor centered at 0. If you're looking at your notes, I'm at the bottom of the first page. That means find a polynomial with degree 6. And so I have f of x is ln x, f prime of x is 1 over x, or for convenience sake, x to the negative 1. F double prime of x is negative x to the negative 2. F triple prime of x is 2x to the negative 3. F, the fourth derivative at x, is negative 6x to the negative 4. The fifth derivative at x is 24x to the negative 5. And the sixth derivative at x is, I think that's 120. I don't know why I didn't write down more than that. Because I need a degree 6 polynomial. But anyway, 24 times 5, I believe, is 120. So it's negative 120 x to the negative 6. All right, now I don't know if you notice these. You'll have to start noticing it. It'll not have to, but it'll sure help your life a lot. 0 factorial is 1. 1 factorial is 1. 2 factorial is 2. 3 factorial, 3 times 2 times 1 is 6. 4 factorial is 24. 5 factorial is 120. 6 factorial is 720. That's about as far as I know, but it's nice to recognize. I can see these factorials creeping in as all these things are happening. Now I'm going to find f prime of 1, and I get 1. Oh, I'm sorry, I'm going to find f of 1, and I get 0. F double prime of 1 is negative 1. F triple prime of 1 is 2. F4 at 1 is negative 6. F5, the fifth derivative, you have to put it in parentheses so you don't have f to the fifth, is 24. And the sixth derivative at 1 is negative 120. So let's get rid of this so we can keep writing. Alright, so I have f of 0, and now remember this one is centered at 1. So really our formula goes like this, and I've been saying it every time. F of 1, f of c, plus f prime of c, which was 1, times x minus c, x minus 1 to the first over 1 factorial, minus f double prime, 1 times x minus 1 squared over 2 factorial. This is plus, 2 times x minus 1 to the third over 3 factorial, minus 6 times x minus 1 to the fourth over 4 factorial, plus 24 times x minus 1 to the fifth over 5 factorial, minus 120 times x minus 1 to the sixth over 6 factorial. This gives me 0. I'm not going to write that down. So I get x minus 1 minus x minus 1 squared over 2 plus, what happens to this? That's 2 over 3, 2, 1. So I just get x minus 1 to the third over 3. This one's going to be 6 over 4, 3, 2, 1. Those cancel, and I just have a 4 on the bottom. X minus 1 to the fourth. That'll keep happening. So I get plus x minus 1 to the fifth over 5, not factorial, it'll all cancel out. And 120 is 5, 4, 3, 2, 1 over 6, 5, 4, 3, 2, 1, so it leaves you a 6 on the bottom, minus x minus 1 to the sixth over just plain old 6. There's no factorial. Now if that's the, so anyway, that's the series that some people memorize for ln x centered at 1. If it's centered anywhere but 0, I really just write it out. On the AP exam, they usually only ask you for 3 or 4 of them. This one's a bit extreme. I can use this to approximate numbers at ln x. When I fill it into here and fill it into here, it converges remarkably on there. All right, on the second page of your notes, we start to see how they ask us on the AP exam. So let's see if black shows up here. All right, so on the second page, you have g as a function that has these attributes. G is a function where g of 2 is equal to 3, g prime of 2 is equal to negative 4, g double prime of 2 is equal to 7, and g triple prime of 2 is equal to negative 5, and they say write a Taylor polynomial centered at 2. So whatever this function looks like, which they don't tell us, whatever this function looks like, it's some sort of curve or transcendental function maybe. They don't give us a name for it, but it's centered over at 2. So it's going to hug it almost perfectly at 2, and then after a while it might leave it. Okay, so my Taylor polynomial goes f of 2, or g of 2 in this case, g of 2, which is 3, plus g prime of 2, which is negative, oh, I'm sorry. It would go g of 2 plus g prime of 2 times x minus 2 to the first plus g double prime of 2 times x minus 2 squared over 2 factorial, blah, blah, blah. That's what I'm doing. And we're doing degree 3. So we're doing a polynomial of degree 3. So I have to get out to the third degree. All right, so I say g of 2 plus g prime of 2 times x minus 2 to the first over 1 factorial minus, or plus, g double prime of 2 times x minus 2 squared over 2 factorial. And then, where was I? G triple prime of 2, which is negative 5, times x minus 2 cubed over 3 factorial. And so now I have my third degree Taylor polynomial that I can actually use to approximate things that are happening on function g. All right, so we'll get a clear slide for this. Sometimes they'll even tell us what I've already taught you. E to the x, I know you've just now learned it, but is 1 plus x. This one has all positives, and 2 factorial and x to the third over 3 factorial. Let's go back and make sure I wrote that correctly. Yeah, okay. So I thought I'd written it wrong. So anyway, it's all the factorials and it does not alternate. It's all the terms. We are using this to find the limit of e to the x minus 1 over 2x as x approaches 0. First of all, if you fill in your 0, you get 0 over 0. And so I definitely, given a choice, would work this with L'Hopital's rule. But I'm not given a choice, and so I'm going to find the limit another way. I'm going to replace e to the x with this polynomial that is mirroring it. 1 plus x minus plus x squared over 2 factorial plus x to the third over 3 factorial, on and on and on, minus 1. So it's e to the x minus 1 over 2x, and take the limit as x approaches 0. My 1's cancel, and then I can start dividing x into all of these. I have x over 2x, which is 1/2. This one's going to leave me an x on the top, x squared. I'm sorry, it's going to leave me an x. X goes into x squared. And that'll leave me x right here. X goes in x squared x times, and I give a 2 times 1 times 2 on the bottom, which is 4. And then I have plus, that's going to give me an x squared on the top over, you don't even really care anymore because you're taking the limit as x approaches 0. That number's going to be 6 times 2, I guess 12. But what happens is now all of these, as you fill in your 0 for your x, you just get 1/2, which is exactly what you would have gotten with L'Hopital's rule also. Okay, so it's interesting, just showing you how the polynomials work. All right, the next example is given a polynomial of degree 2. All they've told me is a plus bx plus cx squared. And they've given me a picture of f. And they ask me what a, b, and c are if they tell me this is a second degree polynomial centered at 0, or in other words, a Maclaurin series. A, doesn't it start off with f of 0 plus f prime of 0 times x minus 0 to the first over 1 factorial plus f double prime of 0 times x minus 0 squared over 2 factorial, and on and on and on. Well, that's the second degree Taylor polynomial. So I know that a would have been created by the first term f of 0. And I can see f of 0 is right here. And I don't know what it is, but the y-intercept is positive. So I know a is, it says tell me the signs of it. And so I know a is positive. All right, I know b comes from the first derivative at 0. And since this graph is increasing, I know its first derivative would have been a positive number. I know c, the second degree, comes from the second derivative over 2 factorial, and this is concave down, so the second derivative would be less than 0. Let's see. All right, and one more example that you might want to write. I don't think it's on your sheet. If I have a Taylor series of 5 minus 3x squared degree 2, and let's say this is a Taylor series that approximates g of x, could be some other transcendental function. The question is, does it have a relative max? Does g have a relative max? And I'm looking at this thing that's modeling it. To decide on, how do we decide on a relative max? You know, I like for you to be very literal. The first derivative would be 0 or undefined, and a way to tell if you have a relative max, the second derivative max would be less than 0. So look at my Taylor polynomial. Taylor polynomials are created by g of 0 plus g prime of 0 times x minus 0 to the first over 1 plus g double prime of 0 times x minus 0 squared over 2 factorial. And so apparently, well, first of all, g of 0 must be 5. Do you see there's no x term? So g prime of 0 would have been 0, which creates a critical number at 0. So that's, first of all, we know we have a horizontal tangent at 0. And from this, our second term, I know g double prime of 0. By the way, it's not 3. We've got to look at how that's created. It's created by this. So g double prime of 0 over 2 factorial came out to be negative 3. So g double prime of 0 is equal to negative 6. But anyway, it's less than 0, so we know our graph is concave down at x equals 0. And so yes, there is a relative max. All right, now pause, and then the next video will be your